about work, energy, and power. So let's first start with work. What is work? Work is defined as, or we can say work is said to be done when a force moves a body through a distance S in the direction of the force. Let's look at this object. If this object was formerly on this, let's say is on a horizontal level, this object was here before, and I apply a force F. This object moves from this particular point to this other point in the direction of the force. So it must be in the direction of the force. So work is said to be done when a force moves an object or a body in the direction of the force. Or we can say work is the product of the force. Work is the product of the force and the distance moved in the direction of the force. So in that case, we can have W. We use the W to represent the work done. Work done equals to force times distance or displacement, as the case may be. The unit of work is Newton meter. How did I get to that level? Force is measured in Newton, and distance is recorded in meters. So the unit of work is Newton meter, and the SI unit is what we call joules. The joule. Now we can see this object move from here to here. The distance S covered. So, and this is the force. We can write this formula as what W equals to F times S. Now let's look at another scenario. If the work, in this case, the force is in horizontal motion and is at the same it's having the same alignment with the distance covered. But in this case, the force is now inclined to the horizontal floor and is inclined at an angle of theta. So we are going to find the horizontal component of the force. This is the force applied. This is the horizontal component of the force applied. So that's Fs. Fs is the horizontal component of F. So looking at this is the opposite side of this right angle triangle, and this is the adjacent side and hypotenuse side. The relationship between adjacent and the hypotenuse side is cos. So cos theta equals to Fs over F. So we make Fs the subject formula. Fs equals F cos theta. So in this case, and we know already that work done is force times the distance. The force here is the horizontal component of the force. We input that formula and we have what? The W equals to F cos theta times S. So we can also write it as what? Fs cos theta. Work done equals what? Fs cos theta. When the force is in the same direction, we say work done equals what? Force times distance. And when it is inclined at an angle theta, we say work done is what? The force times the distance cos theta. Now let's look at this NEGO question 2011 question 13. A load is pulled 5 meters along a horizontal floor by a constant force of 20 Newton, which acts at 30 degrees to the floor. Calculate the work done by the force. We are looking for the work done by the force. So what we are looking for here is the work done. The W is what we are looking for. We have been given the distance S as 5 meters and the force as 20 Newton. Now, the force was inclined at an angle of 30 degrees to the floor. So this representation, so we move the load from here to here, and it covered the distance. The distance it covered was 5 meters. So work done equals to Fs times S, then F cos theta times S. So what's our F? 20 Newton cos 30 times 5. So 20 times 5, that's 100. Then cos 30 is 0.8660. So if you multiply 100 with this, we have 86.6 joules. 86.6 joules of work done. Now let's look at work done in a force field. We already have the idea of a force field. A force field is a field in which the force does not have a contact, does not necessarily need to have a contact with the object in question. We have three types of force field. We have the gravitational force field, the electrical force field or electrostatic force field, and we also have the magnetic force field. But we are not considering the other two now. For this class, we are considering the gravitational force field, the gravitational field. And we know that the gravitational field is a region of space around a mass of a body in which the influence of the gravitational force is felt. So for this case, let's look at lifting a body. When you are lifting a body, let's say this is the horizontal body, horizontal floor. I am lifting a body H, this body or a mass of a body. I'm lifting it from this floor. I'm taking it to a particular height. Let's say the height is H. As the height is H, I have been able to use a force to move this body to a height H. I have done work against the gravity. When you are lifting a body in the force field in the gravitational field, you have done work against gravity, and the force that was applied in overcoming the gravitational force is equal to the weight of this object. And so in analysis here, we have force times distance, and the force equals to the weight. So we're going to represent it with the W. Let's say W. So the weight equals to work done. Let's write this as work done, so we don't confuse the two W's. Work done equals to the weight times height, and we know the weight is equals to what? The product of the mass and the acceleration due to gravity. So work done equals to what? mgh. So when you are asked to find the work done in lifting a body in the force field of the earth, you just make use of this formula. So where your m stands for the mass of the body, the g stands for the acceleration due to gravity, the h stands for the height through which the body was lifted, and the g, of course, is approximately equals to 10.0 meter per second squared. In most cases, you may have 9.8, but you follow the instruction given. If the examiner gave you G as 9.8, make sure you follow it as 9.8. Do not write what is not given to you, so that you can get your full mark. Now let's look at case 2. In case 2, we have issues of falling bodies. Now this object was held at a particular height. Let me use another body. This particular object falls freely under the force of gravity. It means if this thing falls freely under the force of gravity, then work done, the force of gravity has done work on this object. So there's a work done on it because it's moving in the direction of the gravitational force. Yes, so you can see this falling object through height h. The weight is still mg times mg. That's mass times the acceleration due to gravity. So work equals what? mgh. Then when we have a body falling down an inclined plane, and an inclined plane, we look at this, a body falling down an inclined plane. Then we look at the inclined plane. This is the height of the inclined plane, h. This object is moving down an inclined plane. We are not considering the frictional force on the inclined plane now. We are only looking at work done on this body. So, excuse me. This is the angle through which the angle of inclination of the inclined plane. And this is the length of the plane. That's, we are representing it with L. But in calculation, We do not use the L to calculate the work done. We make use of the height through which this object moves, not the length of the plane. So we are going to find h in terms of L. And you know this h is the opposite side of this triangle. This L is the hypotenuse side. So what relates the opposite and the hypotenuse together is the sine theta. So we're going to use sine theta, which is opposite over hypotenuse, h over L. So therefore, h equals to L sine theta. Therefore, we can write work done equals to mgl sine theta. So when you are considering a body that is moving down an inclined plane, we use mgl sine theta.